Welcome to Math 1960. This is uh, Calculus 2. Today we're going to discuss about power series. So power series, convergence, interval of convergence of power series. We'll define a function using power series. We'll use properties of power series. So a variable, a series with variable terms is known as power series. So it looks like this. So as you can say here, most of the time the series start from 1, but now because we introduce x, we're going to start from 0. So it's going to be ace of 1 plus ace of 0 plus ace of 1x plus ace of 2x squared. This is just an example of power series centered at 0. This is an example of a power series centered at c. C here being a number. So we want to determine power series conversion or diversion. For some values of x, power series can reduce into real numbers, like the series studied so far. Like there are some numbers of x that make the power series conversion. Okay, so we will go about finding that x number that makes the power series converges. To find number x for which power series in x's conversion, we will use ratio test or root test. So these would be the main tools we will use to examine the power series conversion at this point. Okay, so now we're going to discuss how do we actually determine whether this one here converges or not. What numbers of x that makes these power series converges. So first we're going to use the ratio test here. So we're going to say ace of 1 is equals to x raised to the power of n over n factorial. Ace of n plus 1, it's going to be equals to x raised to the power of n plus 1 over n plus 1 factorial. So then we find the limit, just like we learned from previous lecture. So we are going to divide ace of n plus 1 over ace of n. That means we're going to have x n plus 1 over n plus 1 factorial times x raised to the power of n. Sorry, since division is going to be multiplication at this time, so we're going to have here n factorial. We're going to have n factorial over x raised to the power of n. So absolute value of that. So since so we're going to say limit as n goes to infinity. So x of n will take care of x of n here. We will have x here, x raised to the power of 1. So we're going to have x on this. And then n factorial and n factorial take care of each other. We're going to have n plus 1 on the bottom. N plus 1, n plus 1. So this diverges. This is going to be the absolute value. This diverges. So we're going to get this one here goes to 0. For all values of x, this limit here goes to become 0 for every value of x. So that means all x real values are allowed here. Makes this one converges. Okay, so we are going to do problem 1 part 2. So we are going to determine at this point whether whether the summation from k equal to 0 up to infinity of k x raised to the power of k over 4k. So we are going to say, what is my ace of n at this point? My ace of n, it's going to be equals to n x raised to the power of n over 4 raised to the power of n. What is my ace of n plus 1? It's going to be equals to n plus 1 times x raised to the power of n plus 1 over 4 raised to the power of n plus 1. So we are going to use the ratio test. Ace of n plus 1 over ace of n, we take the limit of that as n goes to infinity. So for this one, we are going to have n plus 1 times x raised to the power of n plus 1 over 4 times 4 raised to the power of n. So 4 raised to the power of n plus 1 is the same as 4 times 4, 4 raised to the power of n times 4 raised to the power of n over n times x raised to the power of n. So x raised to the power of n and x raised to the power of n cancels out. 4 raised to the power of n, 4 raised to the power of n cancels out. And then we're going to have, so we can pull out the x here and pull out the x. So we're going to have limit as n goes to infinity. So here I'm going to have n plus 1 over 4n, and that should give me x over 4. So in order to this one here converges, for convergence to happen, x over 4 must be less than 1. So the region of conversion is between positive 4, negative 4 and positive 4. So these are the x values that allows for convergence of this allow for convergence. Okay, so we are going to get the eraser. So right now we will discuss part C of the problem. And part C here, I have summation from k equals to 0 up to infinity of k factorial x raised to the power of k. So first we are going to just get ace of n, put it up there, and ace of n plus 1. Okay, so limit as n goes to infinity. Ace of n plus 1 is going to be n plus 1 factorial x raised to the power of n plus 1 divided by n factorial times x raised to the power of n. That should be equals to limit as n goes to infinity of n plus 1 n factorial times x raised to the power of n over x divided by n factorial times x raised to the power of n. So this cancels out. N factorial cancels out. So x limit as n goes to infinity of n plus 1. So this is going to give you, is either going to give you 0 if x is equal to 0. it's going to give you infinity if x is not equals to 0. So the only number that is convergent is when x is equal to 0. Okay, so theorem of convergence, divergence of a power series. If a power series which is summation from k equal to 0 up to infinity of a of k, x raised to the power of k, converges for a number x of 0 equals to not equal to 0, then it converges absolutely for all numbers x for which x less than x of 0. So if it converges for x equal to 0, here, excuse me, here we should have say x equal to 0. So here that means it's going to converge for any number that is less than that. So if it diverges for x greater than x equal to 1, right, it diverges for any number greater than that. Okay, so this is, so if the power series which you have here converges for x equal to 6, then it will converges for x equal to 3, because x equal to 3 is less than x equal to 6. So this power series here diverges for x equal to 4. So then it diverges for x equal to -5, because absolute value of these is greater than x equal to 4. So another theorem, for a power series, there is exactly one thing which is true, is either that x equal to c, this x here is equal to c, or the series converges absolutely for all the numbers x, or there is a positive number r for which the series converges absolutely for all x. So one of these three must be true for any power series. So this is an important method that we need to pay attention to at this point.